we have the last speaker of the conference, Prerna. You have a...
Hi, am I audible?
Hi. Yeah, you're audible.
Okay, can you see my screen?
Yes, I can see it also. So you have around 12-13 minutes and then couple of minutes for questions. So okay, so we're very happy to have Prerna from TIFR, who's going to tell us about astrophysically relevant geodesics in Kerr spacetime.
Thank you very much. First, I would like to thank the organizers for inviting me to present this work. I'm a postdoctoral fellow at TIFR Mumbai, and I'm also a member of Indian Pulsar Timing Array Collaboration. This is the outline of my talk. First, I'll introduce a little bit about Kerr spacetime and how we have different kind of three-dimensional time-like geodesics in Kerr spacetime, and what are their analytic solutions, and then finally I'll summarize and talk about a little bit of application of these analytic solutions. So moving on to the first part, this is a Kerr metric, standard Kerr metric, which was given by Roy Kerr in 1963. This was written in terms of Boyle-Inglis coordinate dr theta phi, where A is the spin of the black hole. So if we talk about the time-like geodesics in Kerr spacetime, that has three conserved quantities. First is energy per unit rest mass, because this metric is stationary metric. And then the another conserved quantity is Z component of the angular momentum, represented by L, because this metric is axisymmetric. And the third conserved quantity is Carter constant, which was derived by Carter in 1968 by showing that the R and theta components of the Hamilton-Jacobi equations are separable, which is equal to the constant called Carter's constant. So before I go into the detail of these geodesics, I first would like to give a small history of time-like geodesics. So first pioneer work was done by Carter in 1968 by solving the Hamilton-Jacobi equation and writing this equation in terms of in a quadrature form. Then Wilkins in 1972 gave a solution for spherical orbits for extreme spin A equal to 1. And Bardeen in 1972 derived the formula for energy angular momentum for circular orbits, and the standard is co-radius, which is in a more stable circular orbit. Then Schmidt in 2002 derived the fundamental orbital frequencies, which are nu phi, nu r, nu theta in the quadrature form. Then Fujita Hikira 2009 gave the first fully analytic form of these equations of motion. And Rana and Mangalam 2019 gave a much simpler analytic solution of the equation of motion in terms of two parameters, which is eccentricity of the orbit and inverse lattice rectum of the orbit, E and mu. And they also discuss various types of orbits. And in this talk, I am going to concentrate on this particular paper. Very recently, Compared et al. 2022 also discussed a very detailed classification of radial motion in Kerr spacetime. So moving on to 3D time-like geodesics. As I told that this spacetime, Kerr spacetime, is axisymmetric. So that tells us that the motion of the test particle is not constrained in a single plane. So the plane of the orbit itself can change. Hence, it leads to three-dimensional Kerr trajectories. So on the right hand side in figure 1a is shown as the eccentric non-equatorial motion. So we can clearly see that the motion is three-dimensional. There is a precession in the z direction, and in the middle I have shown a spherical orbit where the radius of the orbit is constant, whereas the motion in z direction can be seen. On the right hand side, there is a special orbit called separatrix orbit, which is a separation between bound and unbound. So all of these orbits were studied in detail in this particular paper, which I'm going to discuss. So why should we study these orbits? So there are astrophysical application, for example, study of quasi-periodic oscillations, which are the peaks seen in Fourier power density spectrum of X-ray binaries, which is shown in the middle. So this is a Fourier power density of the light curve X-ray binary. So these peaks can be seen at 300 Hertz and 450 Hertz, which are actually indicated the fundamental frequency of oscillation of matter around the black hole. Hence, it is important to study these orbits and their fundamental frequency, their trajectory solutions. Another astrophysical implication is the study of extreme mass relation spiral, where a compact object is spiraling onto a supermassive black hole, and it actually follows a series of Kerr orbits before plunging onto the black hole. Hence, it's important to know the solution for these Kerr orbits. Left-hand side, I have just shown a cartoon picture of X-ray binary where black hole is accreting mass from a typical main sequence star, which actually shows this kind of power spectral density. Okay, so let's talk about the radial motion in space-time first, which is governed by this particular equation. So we can clearly see there is total energy, kinetic energy, and effective potential, which is fourth order in R. So this leads to 4 roots of this particular equation, which are represented by R1, R2, R3, R4. And the radial motion can be of various kinds. So this is a plot of effective potential as a function of R. Horizontal line here is the energy. And the vertical red dotted line is the horizon, radius of the black hole. So we can clearly see here there is a bound orbit between R1, R2. And it can be between R3, R4, but here that radius is inside horizon, so that doesn't matter. The another kind is where there is bound region between R2, R3. And the third kind is where the bound region is either between R1, R2 or R3, R4. So the astrophysically relevant case is only the first kind, because the 2 turning points are outside horizon radius, and that's where we concentrate on. Okay, so the trajectory solution of these orbits, the equations were written in this standard form by Carter in 1968, but they were left in these form, which are integrals. And solving this integral had been a long task, and it had been done by various authors. What we have done is, so we have this, as I discussed, we have these 4 roots, R1, R2, R3, R4. And we write these roots, which are turning points, R1, R2, in terms of 2 parameters, eccentricity and inverse lattice rectum. By using such transformation, it helps us to remove the singularity of the integrants at the turning points. Hence, we use this parameter space, E mu AQ, and we derived an analytic solution for all these integrals. So now I'll discuss various analytic solutions of these trajectory solutions, and also various kind of trajectories. Here I've just summarized the, I can't go into detail of deriving. So I have just summarized that the phi motion, T motion, and the R theta motion, which is coupled, can be written in terms of all these integrals, which are written in the standard standard form in terms of standard elliptic integrals. And all these are actually function of E mu AQ. So as I told, the advantage of using this novel trajectory solution is that it removes the singularity at the turning point of the orbit and also provides us faster computation. Another advantage of using this trajectory solution is that it can be used to derive analytic solution for various types of orbits. Okay, so before going into that, I would like to show the condition for bound orbit in E mu AQ parameter space, which we are using to solve these integrals. So the conditions are given by 3 equations. The first condition is that the integral should be real, which leads to this particular equation. And then the second condition is the peristron point of the orbit should be outside horizon. And the third condition is that energy should be less than 1. And these conditions, when we try to see them in E mu space, it leads to this shaded region, which is the bound orbit region. And this red curve, which is the boundary, is actually representing the separatrix curve, which basically means the separation between bound and unbound. And these extreme points, S and M, are special kind of orbits, which are called innermost stable spherical orbit, and M is marginally bound spherical orbit. They are contradictory to ISCO radius and marginally bound circular orbit, which was derived by Bardeen in 1972. Now, these special radii can be can be shown in this form. So here the red region is the horizon, and I have shown here the ISSO, which is innermost stable spherical orbit, shown in the black color, and the blue is marginally bound spherical orbit. And these are the important radii in Kerr spacetime. And another important trajectory, as I was discussing, is separatrix trajectory. So these are also called homoclinic orbits because as we see from this effective potential diagram, for separatrix orbit, the particle starts from an epiastron point R1. It reaches to the periastron point. Here in this diagram, this trajectory has R1 here, and it reaches to the periastron point where it takes infinite time to reach to this periastron point, which is actually an unstable point represented by Rs. So if we go to T plus infinity or minus infinity, R tends to Rs. And why these trajectories are important? They are very important in the study of extreme mass ratio spiral, because when the transition happens from the inspiraling to plunge, the orbit transits from a separatrix orbit. So it's very important to know the position of separatrix orbits in the parameter space, and that's exactly what we have done. We have got a very nice closed form formulae for eccentricity and inverse lattice spectrum for separatrix orbit as a function of RSAQ, where RS is this particular point for separatrix orbit, which also corresponds to periastron point of the orbit, and the spin of the black hole and Carter constant. And we also showed that these formulae are reduced to the equatorial case when we put Carter constant equal to 0, which were previously derived by Levin and Page-Gries in 2009. And if we want to write the separatrix in a single equation, that also we have written down. So this particular equation gives the solution for separatrix, and it actually helps us to obtain the trajectory solution for separatrix, which were obtained in terms of simple logarithmic and trigonometric functions. There are different another categories also. For example, equatorial eccentric orbits, spherical orbits. We have studied them also. So the trajectory solution that we have already obtained for the non-equatorial eccentric can be further reduced into these form. So I've just shown the equatorial eccentric orbit here and the spherical orbit here. So for spherical orbit, we had also written down the general expression for energy angular momentum as a function of radius of the spherical orbit, spin of the black hole, or Carter's constant. And we showed that these expressions reduced to the standard formula for equatorial circular case, which was first derived by Bardeen in 1972. And finally, as I told, the fundamental frequencies in Kerr spacetime, nu phi, nu r, nu theta, can also be written down because we already have a solution for trajectories and their integrals. And these three frequencies can be written down in terms of those integrals. And they have a very nice closed form given here. So to summarize, all these analytic solutions have made advancements to various orbital dynamic study, which were done by Bardeen, Schmidt, Levin, and Fujita in Kerr spacetime. So if I have to summarize, this is just a summary of all the novel formulae and how they have done advancement in theoretical results. For example, spherical case, we have energy angular momentum and various important radii, and the frequencies of oscillation we have derived. Whereas the Schmidt had studied these expression, but given in only quadrature form, and now we have a fully analytic form. And the trajectory solution, which are useful to derive various other solution for separatrix, spherical case. So the important point here is that these trajectory solution are written in E mu AQ parameter space, which makes this solution simpler and also remove the singularity at the turning points. And finally, the separatrix case that we have studied and this expression for eccentricity, inverse lattice spectrum for separatrix and their trajectory solution also written down. So as I was saying, there are astrophysical applications also, but I do not have time to go into detail. But if you're interested, you can go through this paper, which actually use this analytic solution to study the quasi-periodic oscillation in black hole X-ray binary. Basically, they use the we use fundamental frequency formulae to associate with the frequency of quasi-periodic oscillation in X-ray binary, and also the study of Fourier power spectral density of the light curve of AGNs using these analytic solutions. Thank you for your attention.
Okay, thanks, Prerna. So let's thank Prerna first for a very clear talk. Then maybe we have time. Amitabh has a question.
Yeah, thank you, Prerna, for a very nice talk.
Thank you.
Yeah, actually, this one of the first things you mentioned about connection to extreme mass ratio in spiral. For in that context, one needs to study the motion of a spinning particle, which does not follow a geodesic equation exactly, this MPD equation.
Okay, yes, yeah. So the assumption, so the assumption here obviously is if there is a compact object which is in spiraling, the supermassive black hole is spinning, which is Kerr. But if we want to use this solution in extreme mass relation spiral, there we assume that the compact object, which is can be either void dwarf or neutron star or black hole, that is not spinning. So only in that condition we can use these geodesic solutions.
Yeah, no, but I wanted to ask a little bit more, like, has there been progress in solving that equation? Recently, there were papers by MIT group, just last week, there were a few papers by.
Yes. So yeah, for spinning, also there have been various studies, but I'm not sure if the fully analytic solution is available. Yeah, I am not sure about that.
Thanks.
Definitely, we have fully analytic solution for non-spinning particle. But spinning case, I'm not sure.
Okay, any other questions?
Can I ask one more question? Sorry.
Sure.
So there was also this paper by Edward Liu, the Singapore group.
Yes.
Can you comment on that about what did they do and so on?
Okay, yeah. So so that particular paper talks about phase space also, energy angular momentum, and they define they give the condition and in the phase space how the spherical orbit should look like. But their analytic solution for spherical case, which was given before that itself, I would like to mention that this particular paper also has derived it already. Okay. The point of the analytic solution that I have presented here is that the same analytic solution can be used to derive trajectory solution for all various types of orbit, like separatrix, like spherical, equatorial eccentric. So they are just subcategories. So the main, the most general non-equatorial eccentric solution can be used to derive these subcategory solutions, which they have done definitely, and their solution actually matches with the solution for spherical orbit given in this particular paper. I had checked it and I had matched that numerically the solutions are same, but the analytic form is a bit different. But yes.
Thanks.
Okay. So maybe I can ask a small question. I think maybe following up on Amitabh. So if you for the spinning case, is the Carter constant still conserved quantity? If the particle is spinning?
Okay.
Or is it, I mean, otherwise it will be very difficult, right, to make any progress?
Yes. So yeah, one has to go back and look at if the Hamilton-Jacobi equation is separable or not.
Okay.
I have not done that derivation, but if it is separable, then definitely we'll have a constant which we can call as Carter constant, which should be constant. I can check that.
Okay, thanks. And maybe I missed that, but if you keep the Carter constant positive but take the spin to 0 for the Kerr black hole, I mean, then what is the orbit you get in that case? I mean, is the range of theta anything or?
Okay. So spin, you mean a spin of the black hole to 0?
Yeah, but you keep Carter constant positive.
Okay. See, then the Carter constant doesn't have a meaning because
right, but you can keep it, right? Like you can take it.
We can keep it, but still the motion will be constant in a single plane.
I see. Okay.
Yeah. Okay. It is not going to change the plane of the orbit because there is no particular direction in the space time. So spin is not there. So I can keep Carter constant as I want. So, but it won't matter. So it's not going to precess.
Right, right. So I was thinking range of theta maybe remains unrestricted.
No,
Anyway,
so
yeah,
theta
yeah.
is not going to change. So what we do is that we just take the simpler case, take theta equal to 90.
Okay. Okay.
yeah.
Thank you.
Which
So
makes
if-
kata constant 0.
Okay. Without even taking it to 0, it just disappears from the expression.
Yeah. So that's the assumption. So, but even if we take kata constant positive,
Yeah.
the theta is anyway not going to change.
Okay.
So, yeah.
Okay. So if there's no further question, let's thank Prerna once again.
Thank you.